Hello. In this video, we're really going to dive into the concept of a degree. So let's start with just a basic question. How many degrees are in a circle? We mentioned this in the last video, that if you were to take a circle, you could think of dividing it up into a couple of lines. Each line's a right angle. So you'd have 90, 90, 90, 90. Meaning in the whole circle, you'd have 360 degrees. But, I mean, this raises all sorts of questions, because why is a right angle 90? Well, maybe you say, because a circle is 360 and it goes into 4 parts, and 360 divided by 4 is 90. But this feels sort of like circular reasoning, no pun intended. If we have a right angle being 90, and that gives us 360 degrees in a circle, and we have 360 degrees in a circle, and that gives us 90, I mean, where did it all begin? Now, if you go back to ancient Babylon, the Babylonians measured a year as 360 days. Now, we know that in a year there's actually 365 days. But what they did is they said 360 days is easier for doing math, because you can divide it by 12 into 30 days. And so you can kind of have like 12 equal sections. Each one is 30 days. You end up having to have like some leap months. But they said, you know what, for our purposes, we're going to pretend that the year has 360 days. And I guess, in a full year, it's like a full circle. So maybe a full circle has 360 degrees. So, okay, maybe you could think of it like that. A circle is like a year. It's like a full cycle. If we approximate a year to have 360 days, well, then a circle has 360 degrees. But that still kind of feels made up. I mean, if you think about it, right? Like, what if you were on a different planet that had a different number of days in a year, like maybe Mars? If you were to go to Mars and you were to look up how many days in a Martian year, you would find the answer is 687 days. So maybe if there were aliens on Mars, maybe they would have come up with maybe 700 degrees in a circle. Or maybe they would have said, you know what, this number isn't close to anything nice, so maybe we should just do 100 degrees in a circle. Maybe 100 makes sense. Or maybe we could have said maybe a right angle is like 100 degrees. Because, it's like a perfect 100. I mean, 90 doesn't feel like a full right angle. The number 90 feels weird. Maybe 100 would be good. So then, if we had a circle, which would be 4 right angles, maybe we would get 400 degrees in a circle. And what you should see from this little investigation is that the number 360 is totally made up. This number is made up. There's no reason why there's 360 degrees in a circle, in the sense that it's not required. The concept of a degree is a human invention that we made up, and we said, well, let's make up this thing called a degree, and we'll say there's 360 of them in a circle. But it's not like it's a fundamentally true property of the universe. We just had to make up a number and everybody agree on it. This is what we've done with measurement for a long time. Let me give you an example. If we take a look at this, we might ask, what is a meter? And if we look at this metal bar is a meter. For the longest time, they had a big, long metal bar, well, a number of them, and they were all the same length. They were kept in France. And the way that you know how long a meter is you just look at this bar and you say, that's a meter. And so if you're wondering if your meter stick is correct, you just take your meter stick and you lay it down next to the bar. You make sure that it's the same length, and you say, yes, that is a meter. And someone says, well, okay, so what is a meter? You're like, oh, it's this bar. It's this bar that we made in France, and this is how we know how long a meter is. It's the same length as this thing. And again, you might say, well, this seems kind of arbitrary. Like, what, you found some random piece of metal, you cut it to a certain length, and you just said, hey, this is a meter. And well, yeah, that's kind of how measurement was initially defined. If you think of even something like, like a foot, right? The idea of a foot, how long is a foot? It was like somebody's foot. These are just the way humans measure things. And for the longest time, the thing like a foot might change because one person's foot might be longer than another person's foot, and so these measurements could be all over the place. It's nice to at least have a standard. This meter stick in France is the only meter stick, and we have to all compare ours to this one. But it does feel a little bit made up, and that's important to recognize. I mean, this is even true with numbers. So you might say, like, what is a number? And so here we have the different evolution of the numbers that we use. So for example, we have Brahmi numbers up here. We have some Hindu numbers, Arabic numbers, medieval numbers, and modern numbers. This, to our best efforts, is sort of how our number system evolved. And so you can see at different points, first they had nothing for 0, then they put a 0, then they put a dot, then they put a bigger like kind of circle, right? And then our standard oval. You can see a 1 is maybe horizontal, and then now it becomes vertical. Or maybe we put 2 dashes for 2. For some reason that eventually morphs into this 2. The 3, I think it's almost like you're kind of joining it up, but then this one's sort of sideways, so that's weird. 4 they had as a plus symbol. That was wild. We got 5. So the 6, I can kind of see how it sort of evolves here. The 7. But I mean, the 8, it just takes different forms, and the 9 as well. Different people at different points in time have represented numbers differently. And there's no reason why the 9 has to be this way. There's nothing 9 about this. It's just that we all agreed that this symbol will represent the number 9. But it's made up. And we would be free to make up any other number system. I mean, this is the one we use right now, but you could imagine somebody really loving tally marks. So 1 would be a 1, and 2 would be the 2, 3 would be the 3, right? We could use these to represent our number. That could be the symbol for 4. Or we could come up with some new symbol. Maybe it's going to be a circle inside of another circle. Maybe that would be the symbol for 4, right? Maybe we want to go back to that plus sign. Or maybe we want to join, a couple sides like that. Who knows? Any symbol we want, as long as we all agree, and as long as we all understand what we mean, we could technically create a different number system, a different digit, a different numeral for the number 4. And so because of that freedom that we have, we're actually going to do something for angles. We're going to experience a little freedom, and we're going to make up a different measurement system. So here we go. Let's say a circle has a radius of 1. We're going to find the distance around a circle. All right, so there's our circle. We're going to assume that the radius is 1. And we want to find the distance around the circle. Well, remember the circumference is equal to 2 pi r. That's a formula we learned in school. So 2 times pi times 1, or 2 pi. So the distance around our circle is 2 pi. And what we're going to say is if the distance around is 2 pi, let's take that distance around the circle and let's call that our angle. So if this whole circle has 2 pi in it, well then let's say that is the angle in a whole circle. Okay, well, what would that mean for half a circle, right? If we had a whole circle having 2 pi, how much would be in half a circle? Well, this amount of angle would be half of 2 pi, or just pi. How much would be in a quarter of a circle, right? A right angle. This would be half again, so pi over 2. How much in maybe, let's try something that maybe a 45. Well, this would be half again, so pi over 4. And so we can do these halves pretty good. But what if we wanted to think about like a different angle? Something that we maybe knew before, something like 30 degrees. How would we write that in our new measurement system? Well, what we could do is a little ratio here. If we know that the angle in a whole circle is 2 pi, in other words, our old number system, 360, used to be 2 pi. So we can write 30 degrees divided by our old number system should be equal to some number over 2 pi in our new number system. Well, let's go ahead and cross multiply and see what we get. So 30 over 360, maybe I'll simplify that fraction first. That's going to give me 1 over 12 equals x over 2 pi. I'll multiply over the 2 pi, so 2 pi over 12 equals x, and that will give me pi over 6. So 30 degrees would also be pi over 6. All right, so what about 20 degrees? I'd encourage you to pause the video and give it a try. See if you can come up with the measurement in our new number system. All right, so we can write it like 20 degrees over 360 degrees equals x amount over 2 pi. That's the ratio we set up, right? This is our old number system in degrees, and this is our new number system. We haven't given it a name yet, but in our new number system. And so if we cross multiply, we get 20 times 2 pi over 360. So that'll be 40 pi over 360. We can simplify that as 4 pi over 36. And if we divide that out, we'll get pi over 9. So 20 degrees we could write as pi over 9. Now it's interesting, this new number system is not something that I created. It's actually something mathematicians have been using for a long time. Let's take a look. All right, so if I type in convert 20 degrees to radians, I'm going to get pi over 9. So this new number system that we've been playing around with, it actually has a name. It's called radians. And Wolfram knows about it. The computer knows about it. Lots of mathematicians have been using this. This number system is called radians because it's based on the idea of a radius. And so, yeah, we've got ourselves a brand new number system for angles. Let's go ahead and convert the following degrees to radians. Now again, the way we do this is we keep in mind that 360 degrees is equal to 2 pi radians. That's kind of like our conversion factor. Just like if you were to convert meters to feet or kilometers to miles, you might need to know that 1 mile is equal to 1.6 kilometers. That would be useful for converting between miles and kilometers. Here we need to know that 360 degrees is equal to 2 pi radians. So go ahead and try for each one of these, convert them each to their radian measurement. All right, so I'll go ahead and do that first one. 30 degrees over 360 degrees is equal to some amount over 2 pi. It's going to give me 60 pi over 360 equals x. That's going to give me pi over 6. So 30 degrees is pi over 6. Let's do another one. 45 degrees over 360 is x over 2 pi. It's going to, if I cross multiply 90 over 360, so that's going to be pi over 4. All right. Now 60 will just be double of 30, so that'll be 2 of the pi over 6's, in other words, pi over 3. And 90 will be 3 of the 30's, so that will be 3 pi over 6, which we would write as pi over 2. All right, so we have ourselves a few different numbers, a few handy references. We have 30 degrees, 45 degrees, 60 degrees, 90 degrees. Let's keep going. Go ahead and convert these degrees to radians. So pause the video and give it a try. All right, so we have 135 degrees over 360 is x over 2 pi. Now the numbers start to get a little tricky here. We do 135 times 2, so 270 pi over 360. And then we have to simplify the fractions here. This will give you 3 pi over 4. So it's some good fraction work for you, 3 pi over 4. For the 240, when you work it out, you should get 4 pi over 3. 270 will be 3 pi over 2. And then we just do the 315 for you here. So this will be 315 over 360 equals x over 2 pi. So 315 times 2 will be 630 over 360. Now I like to cancel out the 0, so you get 63 over 36. And then we can maybe divide both of these by, well, they're both divisible by 9. So that will give you 7 pi over 4. So there's our last one, 7 pi over 4. All right, let's keep going. Let's say we got some even bigger degrees, 720, negative 330, 540, 400. Go ahead and pause the video and convert these into radians as well, please. All right, so we'll do the first one here, 720 over 360 equals x over 2 pi. So we multiply it. Maybe I'll simplify the fraction first, actually. 720 over 360 is just 2. So then that will be 4 pi. So this is 4 pi. Negative 330 will be negative 11 pi over 6. 540 should give you 3 pi. And let me do that 400 for you. We'll do the last one together. So we have 400 over 360 equals x over 2 pi. That's going to give us 800 pi over 360. So we could divide by 10 to give us 80 pi over 36. I guess we could divide them both by 4 to start. So that'll give us 20 pi over 36 over 4 will be 9. And then I don't think it simplifies any further. So 20 pi over 9. All right, and let's go the other way. Let's say we have some radians and we want to convert them back into our old measurement of degrees. Well, if we had pi, we could write this as pi over 2 pi equals x over 360. It's the same idea as before, except now we have the radian measure, so we're looking for the degree measure. So we can actually cancel the pi's, and that'll be 1 over 2 equals x over 360. Multiply the 360 over, so 360 over 2 equals x. So x equals 180. Go ahead and pause the video and try the next couple. Okay, so for pi over 4, we'll have pi over 4 over 2 pi equals x over 360. Now that fraction works a little tricky. The pi over 4, the 4 pops down into the bottom, so we'd have pi over 8 pi. Because we take this 4, it pops into the bottom, and then 2 times 4 gives us the 8. Okay, now we can cancel the pi's, and so we have 1 over 8 equals x over 360. Multiply the 360 over, so 360 over 8 equals x. And that's going to give us 45 degrees. Okay, if we do the next one, 7 pi over 6 over 2 pi equals x over 360. So that should give us 7 over 12 equals x over 360. The pi's cancel, and the 6 sneaks into the bottom. Then we have to do 7 times 360 over 12. A little bit of fraction skills here. We're actually not going to multiply the 7 and the 360. We'll divide first because 12 goes into 360 evenly, so that's going to be 30 times. And then this is easier now to get us our 210. So it's easier to keep the multiplication as multiplication and work on simplifying these two numbers and then do the multiplication afterwards. In other words, do the dividing first and then the multiplying last. All right, let's do that pi over 2. So we have pi over 2 over 2 pi equals x over 360. So we get 1 over 4 equals x over 360. You might even be able to just snipe this one. 360 over 4, so we should get 90 degrees. And as you start to get used to some of these, you should see, okay, well the pi is the 180 because I always remember the 2 pi is the 360. So pi over 2 is again half of pi is 90. And as we work with these, you're going to start to get more and more familiar with them. So just popping back to our discussion around the meter. Back when the meter was first created, we talked about how there was this physical object. But if you think about it, it's a little sketchy having a physical object as your definition of the meter. I mean, what if you lose it? What if it gets stolen? What if it gets broken? And so what the international scientific community has been working on is a way to define all of these things, not in terms of physical objects, but in terms of physical constants that we always have access to. So for example here, we can see that the meter is now defined to be based on the speed of light and the second. So let me scroll down here. This here is our fundamental units, right? Meters, seconds, kilograms, moles, amps, kelvins, candelas. These are the 7 physical units that we use to measure things in our universe. And if you notice, they're all based on these other outside ideas. And these are all physical constants that exist not in some basement vault in France, but exist in the universe. So let me scroll down here, and I will show you the information around the meter. So the previous definition of the meter, going way back, was of course that long stick in France. But then the meter had been defined as the length of time that light travels in 1 over 299,792,458 of a second, which is better because that allows us to define the meter not in terms of a physical object, but in terms of something anyone could measure, just the speed of light. And then it was, but the thing is, you might say, well, what is a second? A second is what, like some clock that you have in France in the basement? You have the same problem. So in 2019, the definition was finally updated to be the following. The meter is the speed of light, but the second is defined to be the cesium frequency. So you take a cesium atom and you look at the frequency of that atom, and you end up with this number here on the bottom. So now we have the definition of the meter being in terms of both the speed of light, which we know is a physical constant of the universe that doesn't change, and the frequency of the cesium atom, which also is a physical constant that doesn't change. And now we finally arrived. This was a huge deal. We finally converted all of our measurements into these more pure fundamental physical constants. So the idea here is if we were to meet some alien civilization, we don't have to hope that they have a meter that lines up with ours. We could say, well, measure the speed of light. And they'd say, yeah, we can do that. The speed of light is constant everywhere in the universe. And we'd say, okay, now take this cesium atom. We can count until they know which atom is cesium, because the atom is going to be defined uniquely by the number of protons. And so we can just count like 1, 1, 1, 1, 1 until we find the atom. It might not be called cesium in their culture, but we would be able to talk about the same atom. We'd say count the frequency of that atom, and then now divide these two, and that's going to give you 1 meter. And now we would be able to discuss science. We'd be able to communicate. We would have a shared language because all of our units have been converted into these physical constants. They're based on physical constants, not based on objects that we have stored in a vault somewhere. And so this was a big deal. We also defined the kilogram, right? The kilogram, again, used to be a physical object, and now we have a new definition. So if you're interested, you can look it up, the 2019 revision of the SI system. It was a really big deal. And this is kind of what we've done with our units for measuring angles, right? It's almost like we used to have in a circle 360 degrees. But that feels so arbitrary. It feels like what does that even mean? 360 feels too human. And so we want to be more pure. We want to have a more, general system. And so we say, well, let's make it 2 pi. And if we were to explain this to some alien civilization, we wouldn't have to talk about the number of days in a year. We would simply say, take this circle with radius of 1 and measure the distance around it. And they'd say, we can do that. And we'd say, okay, that distance around it, we're going to call that the amount of angle in that circle. We'll call that 2 pi, and we'll go from there. All right. So what we learned today is radians. And I know it's a little tricky because some of you might say, well, we had that perfectly good system of degrees. Why do we have to learn a new system? But the idea here is that radians are a more pure, and they work better in our math to actually use than just degrees. So we have to learn this new system where 2 pi radians, sometimes called rads, if you want to abbreviate just rad, is equal to 360 degrees. And we use this to then convert all of our old measurements. So for an example here, take 150 degrees and convert it to some amount of rad, or take 2 pi over 3 rad and convert that to some amount of degrees. So pause the video and give that a try. All right, so here we should have 5 pi over 6, and here we should have 120 degrees. And again, the way you do that for the 150, let's say, is you set it up in a little ratio. Then you cross multiply to give you 300 pi over 360. You simplify that as 30 pi over 36. And then we could divide again by 6. So that's going to be 5 pi over 6. For some extra practice, you can look at worksheet 1 and 1.5. Definitely give those a try. And any things to remember, the main thing is, of course, this ratio, but it might also be helpful to remember when you're simplifying things. If you have 15 times 30 over 15, it's easier to just cancel the 15s first, rather than doing 15 times 30 and then dividing it out afterwards. It's a nice little trick for when you're simplifying fractions. All right, hopefully you enjoyed this video, and as always, thanks for watching.